Hey there, and welcome. Today, we are diving straight into the deep end with one of the most fundamental building blocks of multivariable calculus, vectors. So if you're used to just thinking about single numbers, get ready, because this is where math really starts to open up into new dimensions.
So what's the big deal with vectors anyway? Well, up to now, you've probably been dealing almost exclusively with scalars. A scalar is pretty simple, right? It's just a number, like a temperature, 25 degrees Celsius. It tells you how much. But a vector, well, a vector tells you two things. It tells you how much and which way. 25 kilometers per hour is the how much, but that word north, that direction, that's the magic ingredient.
And here's the official definition we're going to be working with. A vector is any quantity that has both a magnitude, and you can just think of that as its size or its length, and a direction. This is a huge deal because it's what lets us describe stuff in the real world, things like force or velocity. We're not just talking about abstract numbers anymore. We're talking about quantities with a purpose and a path.
Now, this next idea is absolutely crucial to get your head around early on. It's called position independence. Just look at these two arrows. They start in totally different places, right? But they have the exact same length and they're pointing in the exact same direction. And what that means is that they represent the very same vector. A vector doesn't care where it starts. It only cares about its length and its direction. That's it.
All right, so now we know what a vector is. The next logical step is figuring out how to actually work with them. So think of these next few slides as our essential vector toolkit. These are the core formulas you're going to be using over and over again.
First tool in the box. How do you make a vector when all you have are 2 points in space? A start point and an end point. It's actually super simple. You just subtract the coordinates. You take the x-coordinate of your final point, B, and subtract the x from your starting point, A. Then you do the exact same thing for the y-coordinates, and boom, that's your vector.
Okay, lean in for this one, because this is easily the most common mistake people make. It is always, and I mean always, the end point's coordinates minus the start point's coordinates. If you get that backwards, you won't get some crazy error message. You'll just get a vector that's pointing in the complete opposite direction, which is going to throw off everything else you try to do with it.
So we know a vector has magnitude, right? The how much part. But how do we actually find it? Well, that's where this formula comes in. You'll see it written with these double bar symbols. And if that formula looks familiar, it should. It's literally just the Pythagorean theorem. You just square each component of the vector, add them together, and take the square root. That gives you the vector's length.
This brings us to a really cool and powerful idea, the unit vector. You can think of a unit vector as the pure essential direction of a vector, with all the length stripped away. By taking any vector and dividing it by its own magnitude, we get a brand new vector that points in the exact same direction. But now it has a length of precisely 1. This little trick is going to be incredibly useful, as you'll see in just a minute.
And one last thing before we get to the problems. You're going to see vectors written in a couple of different ways. Sometimes you'll see this I and J notation. Don't let it throw you. It's super straightforward. The vector I is just a tiny vector of length 1 that points along the x-axis, and J is a vector of length 1 pointing along the y-axis. It's just another way to write the exact same information.
Okay, theory's done. We've got our toolkit. Now for the fun part, let's actually put these formulas to work and solve some problems. We'll start with something straightforward and then ramp it up a bit.
All right, let's start with a classic. Find the vector from point A to point B, and then find its magnitude. So step 1, remember the rule, end minus start. For our x component, that's -4 minus 2, which gives us -6. For the y component, it's 5 minus a -3, which is 8. So our vector is -6, 8. Easy enough. Now for step 2, the magnitude. We take the square root of -6 squared plus 8 squared. That's the square root of 36 plus 64, which is the square root of 100, giving us a final magnitude of 10. Let's try another one. Find the unit vector for v equals 3, -4. Okay, what's the first thing we need? Its length, right? So we calculate the magnitude. Square root of 3 squared plus -4 squared. That's the square root of 25, which is just 5. Now for the easy part. To get that unit vector, we just divide our original vector by that length. So we get 3/5, -4/5. This new vector points in the same direction, but if you checked its length, it would be exactly 1.
All right, time for a trickier one. A problem that's going to make us combine a few of our tools. Let's say you need to find a vector that has a very specific length, maybe 7, but it also has to point in the exact opposite direction of another vector. How would you even start to tackle that? Think about the tools we just put in our toolkit.
And here's how you do it. This solution is a perfect example of why the unit vector is so powerful. Here's the game plan. First, you take your starting vector and you find its unit vector. That isolates its pure direction. Step 2, you want the opposite direction, right? So you just multiply that unit vector by -1. Simple. And finally, step 3, you need a new length of 7. So you just take that reversed unit vector and multiply it by 7. And there you have it, a brand new vector pointing exactly where we want with the exact length we need.
So after going through all of that, what's the one big idea you should really walk away with? If there's one thing to remember from all this, it's that it all comes down to mastering a vector's direction. And here's that key takeaway. The unit vector is your ultimate tool for control. It's what lets you cleanly separate a vector's direction from its length. Once you have that unit vector, that pure direction, you can give it any length you want just by multiplying. Want to make it longer? Multiply by a big number. Want it shorter? Multiply by a fraction. And if you want to completely flip it around, just multiply by a negative number. This technique is going to be your best friend as you get into more advanced problems.
So we've successfully put together our toolkit for dealing with vectors in a flat 2D world. We know how to build them, how to measure them, how to change their length and direction. But, the world we live in isn't flat. So the big question is, what happens when we jump into 3 dimensions? What happens when we add a z-axis? How do our tools change? Well, that's what we'll dig into next time.